Welcome to the deep dive.
Hmm,
Today we're really getting into the weeds, tackling the fundamental building blocks of digital electronic systems.
that's right.
You've shared some, honestly, fascinating material exploring these core components, the things that power everything from your smartphone right up to huge industrial gear.
Hmm.
And our goal today isn't just to list them, but to really unpack the clever ideas
Right.
behind how they work together, how these sort of simple parts create such complex tech.
Exactly. We're looking at those essential bits that make all our digital gadgets tick. And what really struck me in your sources was how they break down these, well, seemingly simple concepts into really powerful tools.
Okay, great. So let's dig in. Maybe start with something called a multiplexer, often just called a MUX, right?
Yep. MUX is the common term.
At its heart, it seems like a pretty ingenious way to handle lots of incoming signals, doesn't it?
Right.
Taking many and funneling them down to just one single output.
It is. Think of it like managing traffic, merging multiple lanes onto one single highway. The MUX acts like the controller deciding which lane gets to go.
Right, selecting just one lane at a time. And how does it make that selection? That's the clever part, I guess.
It is. A MUX has those multiple input lines we mentioned, one output line, and then crucially, a set of what are called select lines.
Slack lines.
And these use binary coded just zeros and ones to tell the MUX which specific input line should be connected to that single output.
Binary.
Yeah.
And there's a direct link between how many inputs you have and how many select lines you need, isn't there?
Absolutely. It's a mathematical relationship. The number of inputs you can handle is always 2 raised to the power of the number of select lines.
Okay, so if you have a 4-to-1 MUX, 4 inputs, 1 output,
Then you need 2 select lines because
Yeah.
2 to the power of 2 or 2 times 2 is 4.
right, and an 8-to-1 MUX.
That would need 3 select lines. 2 times 2 times 2 is 8, and so on.
You could almost picture it like maybe an old rotary switch,
Mm.
where each position you turn to.
Yeah, that's a good analogy.
That position is like the select line combination, and it connects you to a different input number.
That's a great way to visualize it. And if we think about the logic, say for that 4-to-1 MUX, let's call the select lines S1 and S0,
Okay,
and the inputs I0, I1, I2, and I3. The output depends entirely on the S1, S0 combination. If S1 and S0 both 0,
but input I0 gets through.
exactly. If S1 is 0 and S0 is 1, then I1 is chosen. 1 and 0 selects I2, and 1 and 1 selects I3.
And you can map all this out in a truth table, right? Which shows every possible combination of those select lines and what happens at the output.
Precisely.
But what's interesting is that the actual data on the inputs, the I/O or I1 values themselves, they don't really show up in the main logic part of that table, do they?
No, that's a key point. The MUX's logic is purely about which path is open. It doesn't care what data is flowing through at that moment, just that it's allowing, say, I1 to pass through.
So the truth table just shows the selection mechanism.
Exactly. It focuses purely on that relationship. Select lines in, chosen input path out, and from that truth table, we can derive a Boolean expression.
The math's behind it.
Sort of, yeah. It's a formal way to describe the MUX's operation using logic symbols. For that 4-to-1 MUX, it looks something like output S1 S0 I0 plus S1 S0 I1 plus S1 S0 I2 plus S1 S0 I3.
Okay, whoa, let's break that down a little. The S1 prime, S0 prime, that means S1 is not active, S0 is not active.
Correct. The prime or apostrophe means not T or logic 0. So S1 S0 means S1 0 and S0 0. And that combination ended with I0 means I0 passes through only when S1 and S0 are both 0.
And the plus signs mean OR.
Yes, so it's this condition for I0, or this condition for I1, or this condition for I2, or this condition for I3. Only one of those conditions can be true at any time, based on S1 and S0.
Got it. And that kind of mathematical description is useful for what? Designing the circuits.
Exactly. For formal verification, making sure the design is correct, and for the automated tools that engineers use to actually build these things into chips.
Okay, so MUXes are this really fundamental way of selecting data. But they're not just theoretical, are they? Where do we actually, find them doing work?
No, absolutely not theoretical. MUXes are real workhorses in digital systems. A primary use is data routing.
Routing, like directing traffic again.
Pretty much. Imagine data needing to move between different parts of a system, say from memory to the CPU, or from different sensor inputs. A MUX can choose which data source gets onto the main data bus at any given moment.
And often you see them paired with something called a demultiplexer or demux.
Yes, very often. The mux combines multiple streams on a one line at the sending end.
And the demux.
The demux is basically a mux in reverse. It sits at the receiving end, takes that single data stream, and uses the same kind of select line logic to direct the data back out onto the correct destination line. It splits the stream back up.
So mux gathers, demux distributes.
You got it. And this mux-to-mux pairing allows for really efficient sharing of resources, like a single communication channel.
Now, one thing the materials really emphasized was the advantage of this over just, running separate wires for everything.
Yeah.
Lots of parallel lines.
Right, that's a huge advantage. First, the obvious one, fewer physical wires.
Which means?
Less material, lower manufacturing cost, smaller physical designs, think smaller circuit boards, smaller chips. It all adds up.
Makes sense. But there was another point about speed, which seemed a bit counterintuitive. Using fewer lines can be faster.
Yeah, it sounds odd, but it can be. When you have lots of parallel wires running close together, they can interfere with each other electrically. It's called electromagnetic interference, or EMF.
Crosstalk, basically.
Exactly, crosstalk. That interference can corrupt the data signals, causing errors, which might mean you have to resend the data, slowing things down overall.
Ah, okay. So single line or fewer lines with a mux has less chance of that interference.
Much less chance. So the data transmission can be more reliable, potentially leading to higher effective speeds because you don't need as much error checking or retransmission.
That makes perfect sense now. Less noise, clearer signal. Now, one of the sources compared using muxes for transferring data to using shift registers. What's the key difference there?
That's a good comparison to draw out. Shift registers can be used to send parallel data over a single line by shifting the bits out one by one serially.
Right.
But the key difference is selection. A shift register essentially processes all the parallel bits together. A multiplexer lets you choose just one specific input line out of many and send only its data.
So if you don't need data from all the sources at once,
Then the mux is much more flexible and potentially efficient. You just pick the one you need right now, ignore the others. A shift register kind of forces you to deal with the whole block of data.
got it. Choose what you need versus taking it all. Your sources also mentioned the ALU, the arithmetic logic unit inside a processor. How do muxes fit in there?
Yeah, ALUs are a prime example. An ALU performs calculations, right? Addition, subtraction, logical operations like AND or R.
The math brain of the CPU.
Kind of, yeah. Inside the ALU, there's different circuitry for each type of operation. A multiplexer is often used to select which operation the ALU performs at any given moment.
So the instruction the CPU is running sets the select lines on a mux.
Exactly. And that mux then routes the input data to, say, the adder circuit or the multiplier circuit or the logic circuit, depending on what needs to happen. It directs the internal data flow for the calculation.
Like a traffic controller for the calculations themselves.
Yeah.
Very cool. And beyond CPUs, where else? General function selection.
Yes, that's a broad category. Think about any system with multiple sensors feeding data in. A mux can select which sensor reading gets processed next.
Or actuators going out.
Yep, select which motor to control, which valve to open. Another example might be adjusting the gain on an amplifier. A mux could select different resistor paths to change the amplification level. Basically, anywhere you need to choose one option from several possibilities.
So even the basic mux is pretty useful.
Yeah,
But technology always improves, right? Your materials talked about enhancements.
absolutely. A really significant one is adding an enable pin.
Enable pin, what does that do?
Think of it as a master on-off switch for the whole mux. In a standard mux, some input is always selected and connected to the output based on the select lines.
Okay.
An enable pin gives you an extra layer of control. When the enable pin is activated, usually set to a high voltage, or 1, the mux works normally. It selects an input based on S1, S0, etc.
But if the enable is not active,
If the enable pin is deactivated, set low, or 0, then the mux's output is forced to a specific state, usually 0, regardless of what the select lines are saying or what the input data is. It effectively disconnects all inputs.
so you can just turn the whole mux off, functionally speaking. Why would you want to do that?
Couple of key reasons. One source mentioned shared data channels. If multiple muxes or devices could potentially drive the same output line or bus, you need a way to ensure only one is active at a time. Disabling the others with their enable pins prevents conflicts.
Like letting only one person talk on a party line phone call.
Exactly that idea. The second big reason is building larger muxes from smaller ones. This is sometimes called making a mux tree.
Okay, how does that work?
Well, say you want an 8-to-1 mux, but you only have 4-to-1 mux chips available. you can use two 4-to-1 muxes.
That gives you 8 inputs total.
Yep. And you use the original select lines S0, S1 for both 4-to-1 muxes. Then you use a third select line, let's call it S2, to control the enable pins of the two 4-to-1 muxes.
So S2 selects which of the two 4-to-1 muxes is actually turned on.
Precisely. If S2 is 0, it enables the first 4-to-1 mux, handling inputs I0, I3, and disables the second one. If S2 is 1, it enables the second mux for inputs I4, I7, and disables the first. Then you just combine the outputs of the two muxes, usually with an OR gate. The enable pin acts as that higher order select bit.
That's really clever. Way to scale up using existing parts. So the enable pin gives you that extra dimension of control. How does it change that Boolean equation we saw earlier?
It's actually quite simple. You just take the original expression for the 4-to-1 mux and multiply the whole thing by the enable signal, let's call it E. So output EAAND, the whole original expression.
Output E, S1 S0 I0
Yeah.
plus S1 S0 I2 plus S1 S0 I2 plus S1 S0 I2.
Exactly. That shows clearly if E is 0 disabled, the whole output becomes 0. If E is 1 enabled, then the rest of the expression works as before.
And the truth table just gets an extra E column, and the output only follows the S1 S0 selection when E is 1.
You got it.
Okay. Now, one last thing on muxes. A source mentioned building them just using NAND gates. That seems specific. Why NAND gates?
That's a very practical point related to chip manufacturing. There's a fundamental concept in digital logic called De Morgan's theorem.
Sounds important.
It is. One of its consequences is that you can, in theory, construct any basic logic gate, AND, D, OR, not T, etc., using only NAND gates.
Really? Just one type of date for everything?
Yep. Or, alternatively, using only NOR gates. So for a chip manufacturer, if they can optimize their production process to make one type of gate like NAND really, really well and cheaply, they might design entire complex circuits, including muxes, using only that one fundamental building block. It simplifies manufacturing and can reduce costs.
Streamlining the factory, essentially.
Yeah.
Interesting. Okay, so that covers multiplexers selecting one input from many. Let's flip the coin now and talk about digital encoders, kind of the opposite idea.
In many ways, yes. While a mux selects one of many inputs to pass through, an encoder takes an active input signal and converts it into a binary code on fewer output lines.
So many inputs, fewer outputs.
Right. The output code tells you which input is currently active. It's compressing information about the active line into a binary number.
And typically the idea is that only one input is active at a time.
For a simple basic encoder, yes, that's usually the assumption.
And just like muxes, there's a predictable relationship between inputs and outputs.
Same relationship, just viewed the other way. The number of inputs it can handle is 2 raised to the power of the number of output lines. Input equals 10n, where n is the number of outputs this time.
Okay, so if you have 2 output lines
You can represent up to 22 with 4 unique input states. That's a 4-to-2 encoder.
and 3 output lines,
It can handle 23 equals 8 inputs.
an 8-to-3 encoder.
So let's take that 4-to-2 encoder. Input's usually numbered 0, 1, 2, 3. If input number 2 is the one that's active, high, what would the 2 output lines show?
They would show the binary representation of the number 2, which is...
At 10.
Exactly. Output line 1 would be high, and output line 0 would be low. If input 0 was active, the output would be 0, 0. If input 3 was active, output 11. It encodes the active input's index number into binary.
Okay, makes sense. Now, your sources showed a truth table for a simple 4-to-2 encoder, but they highlighted a potential problem, a sort of ambiguity.
Yes, there's a slight catch with the most basic design. What happens if none of the inputs are active, all inputs are low?
What would the output be? Well, with simple logic, the output might naturally default to 0, 0.
But 0, 0, 0 is the same output as when input 0 is active.
Precisely. So just by looking at the output 0, 0, you can't tell, is input 0 genuinely active or is nothing active? That's the ambiguity.
I see. That could be a problem. How do you fix that?
The common solution is pretty neat. You add one more output pin. This extra pin is often called a valid output, sometimes labeled V.
Valid.
Yeah. This V output is designed to go high active only when at least one of the actual inputs, I0 to I3, is active. If all inputs are low, the V output stays low.
So if the main output is 0, 0, you just check the V pin.
Exactly. If V is high, you know input 0 is active. If V is low, you know nothing is active. It clearly distinguishes those two states. The truth tables in your sources likely show this V output column resolving that issue.
That's a clean fix. Okay, so that's the basic encoder, but then there's the priority encoder. What does the priority add here?
Well, the simple encoder relies on that assumption. Only one input active at a time. But in the real world, especially with fast digital signals, It's possible for multiple inputs to go high simultaneously, maybe only for a moment.
And a simple encoder wouldn't know what to do.
It might produce a garbage output or something unpredictable. A priority encoder is specifically designed for this scenario. It assigns a priority level to each input line.
Okay, like a ranking.
Exactly. And if multiple inputs are active at the same time, the priority encoder looks at all of them, identifies the one with the highest assigned priority, and outputs the binary code for that input only. It ignores the lower priority active inputs.
It's got a built-in rule for breaking ties based on importance. How is that priority usually set? Is input 3 always higher than input 0?
That's the most common convention, yes. Higher index number usually means higher priority. So in a 4 to 2 priority encoder, input 0, 1, 2, 3, input 3 would typically have the highest priority. If input 3 and input 1 were both active, the output would be 11 for input 3, and input 1 would be disregarded for that moment.
So input 2 would beat 0 and 1, but lose to 3.
Correct. Though it is possible to design them with reversed priority or some other scheme, but highest priority is pretty standard.
Got it. Now, the truth table for these looked a bit different. Lots of X's in there, don't care states. What do they mean here?
The don't cares. They're actually very important for understanding priority logic. An X in an input column means that for that specific row of the table, it literally doesn't matter whether that input is a 0 or a 1.
Why wouldn't it matter?
Because a higher priority input is already active in that row. For example, in the row showing input 3 active, output 11, the columns for inputs 0, 1, and 2 will often have X's. Since input 3 has the highest priority, its active state determines the output, regardless of what input 0, 1, or 2 are doing.
So the X simplifies the table by showing what's irrelevant in that specific case.
Exactly, and it also helps simplify the internal logic design of the encoder itself. The designers can use those don't care conditions to make the circuitry potentially smaller or faster.
Okay, so priority encoders are definitely more sophisticated. Are there downsides? More complex means more expensive, maybe.
That's generally the trade-off, yes. The logic inside a priority encoder is inherently more complex than a simple encoder because it has to implement that priority comparison scheme.
Makes sense.
So yes, they tend to be a bit more complex to design, potentially use more silicon area on a chip, and therefore can be more expensive to produce. You'd use them where you specifically need that ability to handle simultaneous inputs reliably based on priority. If you can guarantee only one input is active at once, the simpler encoder might be sufficient and cheaper.
Right, tool for the job.
Yeah.
Okay, so we have these encoders. Simple and priority, turning active lines into codes. Where are they used? What kind of jobs do they do?
They're really fundamental in quite a few areas.
Mm-hmm.
One major one your sources mentioned is managing interrupts in computer systems.
Interrupts, like when I press a key or move the mouse.
Exactly. Those are hardware interrupt signals telling the processor, hey, something needs attention. You can connect different interrupt sources to the input pins of a priority encoder.
And assign priorities.
Yes. Connect the most critical interrupts, maybe a power failure warning, to the highest priority input. Connect less critical ones, like a keyboard buffer, ready to lower priority inputs.
So if multiple things happen,
the encoder instantly outputs the binary code for the highest priority active interrupt. The processor sees that code and knows exactly which interrupt service routine to jump to first. It's a hardware-based way to manage interrupt priority.
that's a really elegant use case. What else?
Task scheduling is another big one, very similar concept. Imagine a system juggling multiple tasks. You can represent each task needing service with an input line to a priority encoder.
Higher priority tasks get higher numbered inputs.
Usually, yes. If task 7, high priority, and task 2, low priority, both request attention, the encoder outputs the code for task 7. The system scheduler sees this and services task 7 first. One source gave that example of tasks 2, 4, and 7, active task 7 wins.
It's like embedding the priority rules right into the hardware. Fast and efficient. Your materials also specifically flagged emergency stops.
Absolutely critical application. In industrial control, robotics, safety systems, the big red emergency stop button would be wired to the absolute highest priority input of an encoder.
So nothing can override it.
Nothing. If that button is hit, its signal takes precedence over everything else the encoder might be seeing, ensuring the system reacts immediately to the stop command. Safety relies on that guaranteed priority.
Makes total sense. Now, earlier we talked about mux-demux pairs working together. Can encoders and multiplexers team up too?
No, yes. They can make a very powerful combination. Think about it. The output of a priority encoder is a binary code representing the highest priority active input.
And the select lines of a multiplexer take.
A binary code.
So you feed the encoder's output directly into the MUX's select lines.
Exactly. This lets you do something really neat. First, you use the priority encoder to determine which input source is the most important one active right now. Then, you use that resulting priority code to tell the multiplexer to select and route the corresponding data or signal from that chosen source.
Wow, okay. Can you give a practical example?
Let's use that car example again. Maybe you have sensors for the brake pedal, the accelerator, the windshield wiper switch, maybe the radio volume knob.
Lots of potential inputs.
Right, you connect these to a priority encoder. Brake pedal gets the highest priority. Accelerator maybe next. Wipers and radio much lower.
Okay.
Now, say you slam on the brakes while the wipers are on. The encoder sees both signals, but because the brake has higher priority, it outputs the binary code for the brake input.
And that code goes to a MUX.
Yes, maybe a MUX that selects which sensor data gets priority processing by the car's main computer. The MUX, controlled by the encoder's output, immediately selects the brake sensor's data stream, ensuring the braking system reacts instantly, even while the wiper signal was also technically active. It prioritizes the input and routes the associated data.
That really ties it all together nicely. Okay, so we've covered a lot of ground here. We've dug into multiplexers, these data selectors, these traffic cops for digital signals, and then encoders, the data compressors, turning an active line into a code, often with that crucial layer of priority.
And we saw how they can be enhanced, like with enabled pins on MUXes for more control, or the whole concept of priority in encoders. Basic ideas, but with sophisticated applications.
Right, and it's crucial, as you said in the source of stress, these aren't just isolated little circuits. They are absolutely fundamental building blocks inside the big complex systems we use every day.
Definitely. CPUs, memory and controllers, the routers and switches that make the internet work. They are packed with MUXes and encoders managing the flow of information. That efficient routing and prioritizing is critical to how well those systems perform.
You can really start to see how they'd work alongside other digital components too, like adders or counters or shift registers, to build up even more complex functions.
Absolutely. They're like the specialized components in a larger machine. That ALU example you mentioned earlier is perfect a priority encoder identifying an operation, feeding a MUX to select the right calculation circuit. They're designed to work together.
So maybe a final thought to leave our listeners with. We live in this world that's just drowning in data, processing vast amounts in real time. Think self-driving cars, massive server farms.
Yeah, the scale is incredible.
So how might these core principles, efficient data selection with MUXes, prioritized encoding, how might these fundamental ideas need to evolve or be adapted as systems get even more complex and data-heavy in the future? What are the next challenges in just managing the sheer flow and importance of information at this basic level?
That's a great question. The fundamental need won't disappear, that's for sure. But optimizing them further, maybe finding new ways to combine their functions, dealing with even higher speeds and lower power demands. These basic building blocks will likely continue to be an area of quiet but critical innovation as technology pushes forward. It really is fascinating to think about the future based on these core concepts.